So our concept is Kohlrausch law. In previous videos, what we have learned that to calculate molar conductivity at infinite dilution, in case of strong electrolyte, we can easily calculate by the graph by using Onsager equation, Debye-Onsager equation. But it becomes complicated if we have a weak electrolyte, because in case of weak electrolyte, it doesn't dissociate its ion completely. So to explain Kohlrausch law, first I'm taking an example and in which we will see some observation. Then after that we can conclude the Kohlrausch law. So what scientists have found out that in case of, I'm taking example of KCl, I'm writing here, if I have KCl, the molar conductivity, its molar conductivity is 149.9. And if I am taking a molar conductivity of NaCl, that what we have found that its molar conductivity is 126.5. Similarly, they have taken experimental data for KNO3 and for Na-Na3. So I'm writing their value. So in case of KNO3 it is 145 and for NaNO3 it is 121.6. If I subtract both the values, we will get around 23.4, and here in case of KNO3 and NaNO3, by subtracting these values I will get 23.4. So that was the fascinating thing. Why both are giving 23.4? There must be some logic. So while looking onto the electrolyte, we can see that in case of KCl and NaCl and KNO3 and Na3, we will see that in KCl and Na3 we have a common ion, that is Cl negative, and here we also have a common ion, that is NaNO3. So by subtracting these molar conductivity, we can assume that here this value is because of K and Na. Maybe they both are contributing. Here also we can conclude that K plus and Na is contributing to 23.4. So that was the main concept of Kohlrausch law, that the total molar conductivity for an electrolyte is basically the sum of the ions. It is basically the contribution of all the ions which it contains, which the electrolyte has. So with this concept I can conclude my definition. So it is defined at infinite dilution, because we can only get all the ions at infinite dilution. We are taking molar conductivity at infinite dilution. That's why I'm writing at infinite dilution. When dissociation is complete, it has to be complete dissociation. Each ion makes a definite contribution toward molar conductivity. Of the electrolyte, molar conductivity of electrolyte, irrespective of the nature of the other ion present with which it is associated. Basically, here in the example we can see that both have Cl negative ion. So maybe in first example the contribution is just because of the potassium and sodium ion. Similarly, in second case the contribution is just because of the potassium and sodium ion. So both are contributing equally. That's why we are getting same 23.4 value. So that is the concept. In first case we have KCl, but in second case we have nitrate ion. So it doesn't matter what type of anion is present, what type of cation is present, how both the ions and cations are bounded. So it doesn't matter. The nature of electrolyte, nature of other ion basically doesn't matter. All the ions have some contribution, and that contribution is fixed for that particular ion. So mathematically I can write that if I have, this is the molar conductivity, it is sum of, if I have positive ion, I am representing number of cations present equal to V plus, and number of anion I have V negative. So number of cation into molar conductivity of cation plus number of anion into molar conductivity of anion. So this is very simple formula. So the overall molar conductivity is sum of the cation part into its molar conductivity, the molar conductivity of cation, plus number of anion present in electrolyte into its molar conductivity, the contribution of each component of electrolyte. And this equation we define we define our Kohlrausch law in terms of this equation, and sometimes we call Kohlrausch law as Kohlrausch law of independent migration of ion, because it doesn't matter what type of electrolyte it is always the contribution of each and individual ion. So this is the concept of Kohlrausch law. I'm taking 2 or 3 examples to explain it clearly. If I have K2SO4, here we can see that we have potassium ion, we have number of potassium ion, we have 2, plus we have 1 sulfate ion. So molar conductivity in this case, overall molar conductivity is written as del M. It is equal to number of cation is 2 and the contribution of each cation is del plus naught, plus we have only one anion, the 1 into del negative and del naught. Basically I can put naught. In place of plus I can also write small K plus and sulfate as 4 to negative. In bracket you can also put it into bracket. Now moving to second question, second example. If I have Al2SO4, here we have 2 Al3 plus ion and we have 3 sulfate ion. So here in this case we will, by using Kohlrausch law, we can say that the molar conductivity of electrolyte is equal to 2 into the molar conductivity of cation Al3 plus naught, plus we have 3 anion, then it will be del naught SO4 to negative. So this is very simple concept. It is basically the sum of all the ions. So in place of writing 2 times del naught K plus, I am multiplying del naught K by 2. So that is our Kohlrausch law. So thank you so much.